Hi, in this video, I'll be going through certain techniques of integration that are useful in helping us evaluate definite or indefinite integrals. In the previous video, we have shown you different type of functions and what their indefinite integrals are. So when you integrate like sine, you get minus cosine. And that's because when you differentiate minus cosine, you get sine. And so sine x is the antiderivative of minus cosine x plus a constant c, of course. But what if the function now is not as straightforward as a single function, such as like just say sine x or e to the power x, the exponential function, but it's a mixture where it's like 1 over x squared plus sine x, something like that, something more complicated. Of course, that was a very complicated example. You don't need to try that out for yourself. But that was an example to show that there may be certain functions that are actually compositions that you can identify, such that it makes it easier for you to solve the problem. And the first technique we can use is called the inverse substitution, where we see that x can be substituted by a continuous function in terms of t, and when we do so, it actually reduces the problem to something easier for us to see. And then what we need to note is that we need this x to be inverted. We need this x in terms of t to be an invertible function, meaning it's 1-to-1, and we need its derivative to be continuous. The reason for that is so that when this continuous function is multiplied by this, it's still continuous. And when we sub back in to get x in terms of the final result to be in terms of x, we need to take the inverse, so we need it to be invertible. So what do I mean by the inverse substitution rule? The easiest is to use an example to illustrate my point. For example, you get this 1 over 1 plus square root x. You might be thinking that you can integrate 1 plus x easily because it will be a ln 1 plus x. But now you have a square root x. So what you do is you treat t equals to square root x. And then dx dt now is 2t. Then we just substitute it in to simplify the question, and you realize now you get this, which is simpler to solve. And then you can just resub back. Of course, if you are able to solve this to immediately get to see that this is the antiderivative, you can immediately say so. But it's usually hard to see that's true. And so this inverse substitution rule allows you to replace this complicated expression to make it into a form that is easier for you to see how to integrate. And once you integrate that, you just need to sub back the inverse function to get back in terms of the variable you want. And that's why, and because you resub back an inverse function, you need the original function to be invertible as well. Hence, we can take another look at an example to better strengthen our understanding on how to use it. So for example, you want to integrate 1 over x times 1 plus x to the power 4. Well, you can try out different substitution and you'll arrive with the conclusion that this will be the most straightforward. And so you let t equals to 1 over x. So dt dx will be minus 1 over t x squared, which is just equals to minus 1 over t squared. So dx dt will then equals to minus 1 over t squared. And then when you sub everything in, you replace this 1 over x here with t. Then this part you replace with 1 plus 1 over t to the power 4. You see that it reduces to this form. And this form, well, the quotient, the numerator is a derivative of the denominator. And so you can use a substitution again to resub to get an easier expression, which then when you integrate to get this minus 1/4 ln 1 plus t to the power 4 plus c. And finally, you substitute back what is t in terms of x, which is 1 over t. So t equals to 1 over x. So you resub it back in and you get the expression you want. And you can again verify that this is the antiderivative of 1 over x times 1 plus x to the power 4 through an easy differentiation. And so this rule is very useful when you want to simplify your expression to a form that you can check, that you can integrate easily, more comfortably. Moving on, we have another example, and this is to illustrate another common trick when we are integrating and what type of substitutions are good. So for example, when we want to integrate 1 over 1 plus x squared whole thing squared, the common thing is to replace this x squared with something. So we need to think of a way to replace the 1 plus x squared, or we want to replace x with something, so that 1 plus x squared is more easily solvable. And we see that tangent is a good way, because now 1 plus x squared equals to 1 plus tangent squared t, which is secant squared. And so this reduces into a single term, secant squared. And when you differentiate tangent, it's still secant squared. So now it's secant squared over secant to the power 4t, which means it's 1 over secant squared t, which is equivalent to cosine squared t. And cosine squared t, you can use the double angle formula to get this expression. And when you integrate out, you get this. So t can be replaced by tangent inverse x. But how about sine 2t? Well, sine 2t equals to 2 sine t cosine t. Because you know what is tangent t, you are actually able to figure out what is sine and cosine. So the common trick is we draw a triangle, we label this t, so this is like the angle, and since tangent t is x, it actually represents x over 1, because tangent x is the opposite over adjacent. And so it's x in the opposite side and 1 will be your adjacent side, so that when the ratio is still x over 1. And this will mean that the hypotenuse is square root 1 plus x squared. And this implies that sine x equals to x over square root 1 plus x squared, which is what we did here. Cosine x, on the other hand, is 1 over square root 1 plus x squared. And then you can simplify to get the final result. So this common trick is also a fairly useful one, and I hope you have learned it in this video. You must practice more to understand and know when to use this substitution better, and when and what type of substitution you should use. Now we'll see a second type of technique that is commonly used, and that is called integration by parts. And that's basically using the idea of the product rule. When you differentiate du and v, when they are multiplied together, you get du dx times v plus u times dv dx. And so what you want to know is when you want to integrate this, it's become uv. And this portion, let's say you only want to keep one side, then it is actually uv minus the integral of something else. So when do we use integration by part? Is when we have two terms multiplied to each other and you want to keep mount them and integrate the other first. And that's why, because this term will become v, so you're keeping this, integrating this. So a good way to remember is the notation KIID. So you keep integrate, minus away, an integral of an integrated term times the differentiate. So it's keep, integrate, differentiate. That's how I remember it. You can find other methods of remembering how the integration by parts formula, but hopefully after more practice you get a hang of it. So for example, we want to integrate ln x. Well, we don't know how to integrate ln x, or else we have already done so. So what we do is we keep ln x and integrate 1, because it's multiplied with 1. So it's keep, integrate 1 becomes x, minus integrate So integrate is x times differential of ln x is 1 over x. This part becomes 1 and you can integrate that easily to be minus x. And hence, the integral of ln x is actually x ln x minus x plus c. So another thing to take note is that when you are using the integration by parts, this term might still be hard to integrate and you need to use integral by parts again. You cannot now say that you want to integrate u and keep v constant, because it will just result in an expression where it's an integral of du dv dx again. If you think about it, because if you now you're keeping u constant and integrating dv dx, if you were to replace the order, so now you to solve this, you went to integrate u du dx and differentiate v, you'll see that the uv's will cancel out, and then what you're left with is back to the original expression, which is a circular idea. So I'll illustrate that in subsequent examples, but I hope that is clear for you. So we move on to another example to again practice our integration by part skills. So let's say we want to integrate x sine x dx. Well, we can choose either to differentiate or integrate, but usually with enough practice you'll know which one to do. So let's say we want to differentiate x, so that means we keep it first. So x sine x will just equals to keep x, integrate sine x, which is minus cosine, minus cosine x times the differential of x, which is 1, which is y is plus integral of cosine x again. And now we know how to integrate cosine x, which is sine x, and we're done. So you can see how integration by parts helps us when we have terms that are multiplied together, functions that are multiplied together, and we're not sure how to integrate all of it at once. So we can check out this example, and here I want to illustrate another trick and illustrate the remark that I made earlier. So we want to integrate e to the power x sine x. Well, we can do either way. Let's just say we keep ex, we integrate sine x, so it's minus cosine x. Well, that is minus cosine x times differential of ex, which is ex. So this expression now is minus e cosine x plus cosine x times sine ex integral. We don't know how to integrate this again, but we can do the same thing of integral by parts. But remember, in our earlier one, we differentiated ex, so we need to continue differentiating this term over here. So we keep ex, differentiate cosine x, which is minus sine x and then we integrate the integral, so it's minus sine x, which I change here to a plus, and then you differentiate, ex, which is back to ex. So now that you have this expression, we can move this over to the other side. Because this is still minus integral of sine x ex, so what we want to do is now we can bring this over to here. And that's another common trick, is where you're able to realize that this integral appears again and then just bring it over, so they're equal because they're the same integral. So now you get 2 integral of ex times sine x, which equals to this, minus ex cosine x plus ex sine x. So because in the earlier example you differentiated ex, you need to differentiate ex again and integrate cosine x, which is just sine x. And then after you bring it over, you just divide by 2, and that's your antiderivative. Oh, plus c, of course. And so that is how usually we will perform integration by parts, and if you just practice more, you'll get the hang of it. If you want more practice, remember to check out the textbook, or you can watch Black Pen Red Pen's YouTube channel. Now, let's move on to another technique which is commonly used, is the trigonometric substitution. And this is a very simple technique, and it might not always work, but usually it works. Is when you recognize that you have a square root of a squared minus x squared, because a squared minus x squared is something like your Pythagoras, if you understand it. So it can be a squared minus x squared equals to some term you want. Then x squared plus y squared equals to a squared. Then, so you want to substitute the x to make it into a very nice single term, and usually you substitute sine, so that this term will become a squared cosine squared t, which just becomes a cosine t. And if it's a plus, well, then you use tangent, because it becomes secant. And you can see that if it's x squared minus a squared now, use secant so that it becomes tangent. So these are, I would say, not really techniques, but after a while, you'll get the hang of what to substitute in. And so we can see a very common example, such as integral of square root 1 minus x squared. We sub x equals to sine t, and we get actually this following over here. This is just cosine squared t. Use the double angle formula to make it into easier terms to integrate. And then you get your integral. And then we perform the triangle trick again to find what is this cosine t and sine t easily. And you see this the following result. So doing substitution is really about getting a hang and being familiar with the type of questions that is usually asked. And if you get to see it quickly, then that's good for you. If not, you just need to play around with different substitutions, and you'll eventually get the one that helps you integrate it. So just as I said, this is just one type of substitution. You might not need one to sub sine t at certain times. It really depends on the context. So another type of technique I'm going to teach you now is the integration of rational functions. So why would I say this? Is because rational functions are able to be broken down into easier terms to deal with. So a rational function is just a polynomial over a polynomial, such as the following. And if your proper rational function, means your degree above is strictly smaller than the one below. And there's actually a theorem, while we'll not prove it, that every rational can be expressed as a sum of partial fractions. So it means it can be added with a quotient plus a proper rational function. So this quotient is a polynomial, and we can easily integrate polynomials. It's just bringing the power up, dividing by the power. So how do we deal with the rational function, proper rational function then? Well, another theorem is that if it's a proper rational function, and let's say x plus a is a linear factor of the denominator with multiplicity r, it means it's like bx equals to x plus a to the power of r times some other quotient, then it can be actually factorized out into r terms. Below is x plus a, and then x plus a squared all the way to x plus r, a to the power of r. And then if it's a reducible quadratic factor, then it can also be expressed out, but now the numerator is a linear term instead of is a degree minus one term than the denominator. Like how if you have just a linear factor, then the degree is 0, so it's just a constant. So it's best I illustrate this with an example. So for example, 4x over x cubed minus x squared minus x plus 1. We can see that the denominator can be factorized into this form. And so the partial fractions is 1 over x plus 1, because it only appears once, there's only one term. And since x minus 2 is to the power of 2, it has x minus 1 plus 1 over x minus 1 squared. and it's some constant that you must solve. So the partial fraction form is this. So how do we solve it? Well, we just make it into a common denominator, and we see that the numerator must equal. So we equate this with 4x and compare coefficients. And then we solve the linear system to get certain values, and then we just integrate them afterwards, which is easier to do because 1 over x plus 1 we can integrate with the ln function. Here also ln function, and here is just a power function with minus 2, so it's just minus 1 divided by minus 1. Bring the power up, plus 1 divided by the power now. And you can see how this way of solving proper rational functions is much easier than explicitly solving from here. Our last example we want to show is the use of the universal trigonomic substitution. And really, this is when there is a function that is expressed in terms of, so the original function is like some very difficult trigonomic function that you don't know how to integrate. And the trick is you just integrate t to equals to tangent x over 2. So if you use this substitution always, then sine x is this and cosine x is this, and then you're basically able to reduce that function into some sort of rational function at the very least, which then you can integrate using what we have already done for integrals of rational function. And then you just have to resubstitute that x equals to tangent inverse t times 2. So let's take a look over here. So you just let t equal to tangent x over 2. You don't care how this is. Then you show that secant is this value. When you integrate now, you get actually this, which is a rational function. You're able to break it into simpler partial fractions, in which case you can just integrate it easily to be lns of something, and then you recognize that actually there's a repeated term, and that ln 1 plus t over 1 minus t can be split into 1 plus t squared plus 2t over 1 minus t squared. This portion is secant x, and this portion is tangent x. And hence, you get ln secant x plus tangent x as the antiderivative of secant x. So you can see, you just need to apply this substitution, and it usually works to make it easier for you to integrate. If it doesn't, then you just need to try different other techniques. So for example, you just sub t equals to tangent x over 2 again. You simplify this into the next expression over here, which can be further simplified into this. And we can just see that this expression now is easier to integrate. And that's basically the gist of solving an expression with multiple trigonomic functions inside, which you just do the standard trick of substituting t equals to tangent x over 2. And really, with all this substitution, with integration by parts, with integrating rational function, it comes with practice, and the more you do so, the better you'll be. So remember to practice them, and I'll catch you in the next video. Thank you.